Organic light emitting diodes, OLEDs. I'm Nicholas Edwards, and I'm discussing OLEDs. In principle, OLEDs essentially work by passing a current through a material and this generates light. Our OLEDs consist of three basic components. They have an anode, they have a cathode, and they have an organic layer. All these layers are split up further into subcategories. The organic layer is categorized into the emissive layer and the conductive layer. The cathode produces negative charge carriers in the EIL layer, where the anode produces positive charge holes in the HIL layer. The electrons meet the holes in the emission layer. The ETL and HTL are electron blocking layers. Now these manipulate the energies of the HOMO and LUMO to make it more likely for the electrons and holes to combine. The HTL layer transports holes and blocks electrons, whereas the ETL does the opposite of this. So it transports electrons and blocks holes. In order to choose a molecule for the HTL and ETL layers, I must consider the energies of the HOMO and LUMO, as if they are not the right energies, this will not work. Right, okay, first I need some data to decide whether the molecule is going to be categorized as HTL or ETL. So I get my molecule file, yeah, and then I go into Avogadro. I import the desired molecule into Avogadro. My calculations are going to be run in Orca. So I need an Orca input file in order to insert that into Orca and run the simulation that I need to simulate. So I open up Orca. The first thing I need to do is change the task so I have geometric optimization. Right, so we're on the next bit. This is where the Orca input file comes into use. So we upload the Orca input file into the atomic structure. Then we change the coordinates to Cartesian. After that, depending if we have a cation or an anion, we change the spin and the charge to fit the desired compound. Okay, after doing that, we click next and we go into the XC potential. We change that to B3 LYP, named after Lee, Young and Parr. Then we change the basis set to 631G. Now I tried to run these simulations with geometric relaxation on, but it just wasn't working for me, so I had to turn it off. Alright, so we've run the simulation now. We're in output log. This gives us all the data we need. If we want the overall energies, we change the output log to energy. Right, so I'm going to refer back to this molecule as one just to make life a little bit easier later on. So this is the data we have from NanoHub. We can see that the single neutral is the lowest in energy. Therefore, this will be the ground state. So we have the electron affinity. This would be the singlet, so the ground state minus the cationic state, which is minus 175 kilocal. We have the ionization energy. This will be the singlet, so the ground state again minus the anionic compound. So this will be minus 12 kilocal. So I'm going to be referring back to this molecule as 2. We have all the data we have from NanoHub, same as we had previous. We have the electron affinity, which is minus 139 kilocal. We have the ionization energy, which is minus 30 kilocal. Now I've done some comparisons down the bottom. The triple neutral minus the single neutral energy difference is 12 kilocal. The triple neutral 2 minus the single neutral 2 is 8.4 kilocal. Right, so I have been tasked with working out which molecule is best suited for HTL and which molecule is best suited for ETL. So how am I going to do this? You can see that the HTL's HOMO and LUMO are higher in energy than the ETL's HOMO and LUMO. So that means I'm looking for the least negative value for the HTL. If we look, let's take the triple neutral 2 for an example. We can see there that triple neutral 2 is higher in energy, so less negative than the triple neutral 1. Therefore 2 will be the HTL and 1 will be the ETL. Right, so I've plotted the HOMO and LUMO molecular orbitals in VMD and I've color coded them red and blue. This is for the molecule 1. And this is the HOMO and LUMO for molecule 2. So now we're on to alpha helical protein stretch. When a single polypeptide twists around itself, hydrogen bonds are formed at every fourth residue. This also links the oxygen and nitrogen atoms, forming parallel arrangements. All of this together stabilizes the structure. I have been tasked to simulate this structure in VMD and answer some questions on it. We want to simulate this structure stretching like a spring. So we'll have a tensile strength and it'll have a force constant K. So we go to NanoHub. We open StretchMol. We upload 3 files: the initial geometry, the structure file, and the fixed atom file. We want fixed atoms to be on. Now we upload an SMD parameter and we change the x, y, z directions and the velocities to, as you can see there. So next we go to simulation parameters and we upload a file that we want to use. Then we go to number of steps. I've done 2. I've done one for 5,000 and I've done one for 10,000. Essentially, this changes the speed of what your simulation should run at. So we run the simulation and we want to save it as a VMD movie file. Now we want to load that VMD movie file into VMD. You unzip the file, that's the first thing you've got to do. And you go to File, you go to New Molecule. You upload the PSF file first. Now you have to program VMD to tell it how you want the molecule to move. So you want to load data into molecule. You select the DCD file and you load it in. This is what you get for the 10,000 steps. You can see the protein stretching in the second photo compared to the first photo. Now you can see the protein stretch from left to right for the 5,000 steps. You can see the frame rate is lower. So that means this will be a lot quicker than the previous one. This is the molecule in the z-axis. Okay, so I've put the protein structure as to display as a cartoon, so we see it a bit more clearly. As the protein stretches, we can see the water molecules stick into the protein. This is due to the protein containing a lot of electronegative atoms, and a lot of atoms that are capable of hydrogen bonding. So when they bond to the water, it makes it harder for the water to separate from the protein, so they end up sticking to it as the protein unravels. So that was my presentation on computer coding. I hope you enjoyed. Thank you.